this equation 4.5 actually neglects changes in kinetic and potential energy. So, if you are neglecting the changes in kinetic and potential energy, you can write the first law of thermodynamics as U2 minus U1 is equal to 1 Q2 minus 1 W2, where U1 and U2 are the internal energies of the system at the beginning and at the end of the process, and 1 Q2 is the net heat transfer during the process, and 1 W2 is the net work transfer during the process. So, this is the first law of thermodynamics for a closed system undergoing a process. The same equation can be written in terms of specific quantities. For example, all that we have to do here is we have to separate out the mass. That means the total internal energy U2 can be written as mass into specific internal energy U2. Similarly, the total internal energy U1 can be written as mass into specific internal energy U1. So, the 4.5 equation 4.5 can be written as m into U2 minus U1 is equal to m into 1 Q2 minus 1 W2, where 1 Q2 and 1 W2 are specific heat transfer and work transfer rates. Now, let us define an important parameter called flow work. So, whenever a fluid enters or leaves a control volume, it has to do certain work. For example, when a fluid is entering into a control volume, it has to do certain work against the pressure of the control volume. There will be some fluid in the control volume which will be exerting some pressure. So, when this fluid element from outside has to enter into the control volume, it has to enter against a force because of the pressure of the control volume. So, some work will be done during this process. This work is known as flow work. Similarly, when the fluid leaves the control volume, it again has to do some external work against the pressure exerted by the surroundings. So, again you have a flow work. So, it can be shown that the flow work can be or specific flow work is given by the product of pressure and specific volume existing at a point. Now, what is the use of this flow work? Using this flow work and internal energy, we define a very important property called enthalpy, and the specific enthalpy small h is an intensive property of the system, and it is given by h is equal to U plus PV. That means enthalpy of a system is equal to the summation of internal energy plus flow work. Now, this figure shows the first law of thermodynamics for an open system. So, here we have the system. So, I am showing the control, I am sorry, here we have a control volume, and I have shown the control surface or boundary of the control volume, and to this control volume m1 amount of mass is entering. That means the fluid is entering at a rate of m1, and at that condition, that means at the inlet it has an enthalpy of h1 and its velocity is v1, and its height difference with reference to a datum is z1, and it is leaving the control volume at a mass flow rate of m2 with an enthalpy of h2 and with a velocity of v2 and a datum head of z2, and E is the energy of the control volume, and Q is the rate at which energy is entering into the system by means of heat transfer, and W is the rate by which work transfer is being done. That means W is the rate of work transfer and Q is the rate of heat transfer, and the arrows show the direction. And if you apply the conservation of energy or first law of thermodynamics to this kind of an open system, you end up with this equation. This equation on the left hand side you have dE by dt, which is nothing but the rate at which the energy of the total energy of the system is changing. So, and on the right hand side you have quantities which signify the energy flux into the system, net energy flux into the system. For example, this term is the net energy flux out of the system because of the mass flow. For example, if m2 is 0, this term will not be there. So, this accounts for the energy flux out of the system because of mass transfer at the outlet. Similarly, this term, the whole term, accounts for the energy flux into the system because of the mass flow into the system, and W, as I said, is the work transfer rate and Q is the heat transfer rate. So, this is the general energy equation for any open system. So, here we are not assuming anything about the steady state or anything, right? That means it is applicable to a steady process as well as an unsteady process. Now, let us apply this to a steady process. In steady process, what happens is the energy of the system and the mass of the system remain constant. That means they do not vary with time. That means time does not come into picture. So, mass should be conserved and energy should be conserved. That means whatever mass is entering into the control volume must leave. That means M1 should be equal to M2. And since the energy, total energy of the system E is constant, dE by dt should be 0 because energy is not changing with time. So, if you are applying these simplifications, you get the first law for open systems in steady state conditions. So, here again you have this is the rate, on the left hand side you have the net rate at which energy is entering into the system because of mass flow, and on the right hand side you have Q dot and W dot. Q dot stands for net heat transfer rate, specific heat transfer rate, and W dot stands for net work transfer rate per unit mass. So, this is the first law of thermodynamics for an open system in steady state, and this is also known as steady flow energy equation or SFEE. This is a very important equation and we will be using this equation repeatedly during this course. Now, let us come to the second law of thermodynamics. The second law of thermodynamics is a limit law and it gives the upper limit of efficiency of a system. That means it tells you under the existing circumstances what is the maximum possible efficiency that you can think of. So, it sets an upper limit on the possible efficiency of any device or a system, and it also decides the direction of the process. That means second law says that certain processes take place only in certain direction, they cannot take place in the reverse direction. That means second law sets the limit and it also sets the direction of any process. A very simple example is when you leave a cup of hot coffee. This is a very common example people give for second law of thermodynamics. When you leave a cup of hot coffee on the table, its temperature reduces and coffee becomes colder. So, this is the spontaneous way in which the process takes place, and the reverse process is not possible. For example, the hot coffee cannot become hotter by taking heat from the surroundings. That means this process has only one direction. Okay, so the arrow points in only one direction. So, this is not violating, for example, transfer of heat from the surroundings to the cup of coffee is not violating the first law of thermodynamics, because first law of thermodynamics only accounts for the energy transfer. So, even though it is not violating the first law of thermodynamics, you know that it cannot happen. So, this is one of the statements of second law of thermodynamics, because it says that a hotter body cannot become still hotter by taking heat from the surroundings. So, this is one of the directional aspects of second law, and second law also defines a very important property called entropy. Now, the second law of thermodynamics has certain statements. One is what is known as a Clausius statement. So, what is this Clausius statement? It says that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a cooler body to a hotter body. What it means is you cannot have an ideal refrigerator. For example, you cannot have a refrigerator which does not take any power from the surroundings, but it continuously functions. That means it maintains a low temperature inside without consuming any external power. We know that it is not possible. So, this is in simple terms the statement of Clausius, or one of the second law statements. Let us look at the other statement. This is known as Kelvin-Planck statement of second law. This says that it is impossible to construct a device, basically an engine operating in a cycle, that will produce no effect other than extraction of heat from a single reservoir and convert all of it into work. Basically, what it means is you cannot have a heat engine operating in a cyclic manner which has an efficiency of 100%. That means all cyclic heat engines will have efficiency lower than 100%. How do you say that efficiency cannot be lower than 100%? Because the Kelvin-Planck statement says that for a cyclic heat engine to operate, the heat engine has to interact with two thermal reservoirs. That means it has to take from a high temperature reservoir and convert a part of it into work and reject the rest of it to the a low temperature reservoir. And if you are applying first law of thermodynamics to this cycle, you will find that the efficiency which is given by the work output divided by the heat input will always be less than 1, because work output will always be lower than heat input, since some part of the heat has to be rejected to the surroundings. So, in a nutshell, the statements of second law, they basically say that an ideal refrigerator cannot exist. This is the statement of Clausius, and an ideal heat engine cannot exist. This is the statement of Kelvin-Planck. And second law of thermodynamics also introduces what is known as irreversibility, and it distinguishes between reversible and irreversible processes. So, let us define now reversible and irreversible process. A process is said to be reversible with respect to the system and surroundings if the system and the surroundings can be restored to their respective initial states by reversing the direction of the process. That means by reversing the heat transfer and work transfer. The process is irreversible if it cannot fulfill this criteria. That means let us say that a system has undergone a process 1 to 2, and now the process 1 to 2 can be said to be reversible if you retrace the path. That means you travel from 2 to 1 and arrive at 1, then there will not be any change either in the system or in the surroundings. Of course, there will not be any change in the system because you are coming back to the same initial state, but there should not be any change in the surroundings also. Even though there is no change in the system, but there are change in the surroundings, then the process is no longer reversible. That kind of a process is called as irreversible process, and you find that all actual processes are irreversible processes. Now, what causes the irreversibility? Why processes are irreversible? There are several causes. First cause is friction. You cannot avoid friction whenever you have a sliding or rotating motion. So, and the friction is what leads to irreversibility. How does it lead to irreversibility? For example, you take the mechanical this thing, a piston is moving in a cylinder and there will be friction between the piston and the cylinder. So, during this process what is happening? Some mechanical energy is converted into heat because of friction. So, this is the direction of the process. Now, if you want to reverse it, it is not possible to convert all the heat into work without making any change in the system or surroundings. That means whatever work you have lost, it is lost irreversibly. You cannot get back everything without making any change in the systems or surroundings. So, friction is one of the major reasons for irreversibility. What are the other reasons for irreversibility? Heat transfer through a finite temperature difference. We will see later that for any heat transfer to take place, a finite temperature difference is required. That means heat will always flow from a hotter body to a colder body, and you cannot simply reverse the process. That means whatever heat has flown from a hotter body to colder body cannot flow back without making any changes in the system or surroundings. In fact, that will be a violation of Clausius statement, because Clausius statement says that if you want to transfer heat from a lower temperature body to a higher temperature body in a cyclic manner, some external work has to be done. That means some change must take place in the surroundings. So, heat transfer through a finite temperature difference is an irreversible process. And another example of irreversible process is mixing. For example, you are mixing two different gases. I am mixing nitrogen gas with oxygen gas. Then it is a highly irreversible process, because I cannot simply separate them out just like that without making any change in the system or surroundings. So, this is another example of irreversibility. Like that, there are many other causes for irreversibility. Resistance when current flows through a conductor. Like that. Okay. Since all these cannot be avoided in actual practice, all actual processes are irreversible processes. Now, let us define a heat engine. This is very important concept in thermodynamics. A heat engine is a device that operates in a thermodynamic cycle and does a certain amount of net positive work through the transfer of heat from a high temperature body to a low temperature body. So, let us look at it carefully. So, basically a heat engine is a thermodynamic cycle, and what does it do? It does a certain amount of net positive work. That means it produces certain amount of work. And how does it produce? It produces it by a transfer of heat from a high temperature body to a low temperature body. This is perfectly in accordance with the second law of thermodynamics as per the Kelvin-Planck statement. What is the example of a heat engine? A steam power plant is an example of a heat engine. In a steam power plant, typically water is used as a working fluid. So, the working fluid water will be flowing throughout the steam power plant in a cyclic manner, and during this cycle it takes heat from the boiler at a high temperature, and then it converts a part of it into work in the turbine and rejects the remaining part in the condenser. And again it gets pumped and comes back to the original state. So, this is one example of a thermodynamic cycle. Now, the other engines like IC engine, for example, internal combustion engine, in a strict sense it is not a thermodynamic cycle, because the working fluid does not come back to its original state. So, it is not a thermodynamic cycle, it is purely a mechanical cycle, because only the mechanical parts undergo cycles, not the fluid, because you take air and fuel, and what you get out of the engine is not air and fuel, but mixture of combustion gases. So an IC engine in strict thermodynamic sense is not a thermodynamic heat engine. Now let us look at refrigerators and heat pumps. A refrigerator is a device that operates in a thermodynamic cycle and transfers a certain amount of heat from a body at a lower temperature to a body at a higher temperature by consuming certain amount of external work. I am sure that all of you know what a refrigerator is and why do we need a refrigerator. A refrigerator is used for storing food products, as I mentioned in the last class, and a refrigerant system can also be used for providing cool air, cold and dry air for summer air conditioning. So basically a refrigeration system provides cooling. So how does it produce cooling? What happens inside a refrigerator? Inside a refrigerator, what it does is it takes heat from a low temperature reservoir and it pumps it to a high temperature reservoir. Now according to the Clausius statement, this cannot happen on its own, so some external work has to be done. So a typical refrigerator consumes external energy and pumps heat from a low temperature body to a high temperature body, and the useful output that we are looking from a refrigeration system is cooling effect. Now a heat pump is hardware wise is exactly like a refrigerator, but what is the difference between a refrigerator and heat pump is, in a refrigerator we need a cooling effect, whereas in a heat pump we want a heating effect. That means in a heat pump we are not interested in the heat extracted at the heat sink, but we are more interested in the heat rejected at the high temperature level. So typically if you look at the practical application point of view, a refrigerant system can be used for summer air conditioning, whereas a heat pump system can be used as for winter air conditioning. Now let me show this animation here shows yeah, so here we have a heat engine, a heat pump and refrigerator. Here HE stands for the heat engine, and as I explained just now, what is it doing? It is taking heat QH from a high temperature reservoir which is at a temperature TH, and it is converting a part of it into work WHE, and it is rejecting rest of it, that means QC, to a low temperature heat reservoir which is at a temperature TC. In a typical steam power plant, the high temperature reservoir is the boiler of the power plant, and the low temperature reservoir is the condenser. Ultimately the heat from the condenser is rejected to the ambient. So here the TA shows the ambient temperature. So the condenser temperature should be slightly higher than the ambient temperature, so heat can be ultimately lost to the ambient. So it is a cyclic device, so that is what the rotation shows. And if you apply the first law of thermodynamics to the heat engine, what do you find? You find that WHE should be equal to QH minus QC, and if you define the efficiency as the output divided by the input, then it is equal to WHE divided by QH, which is equal to QH minus QC by QH. Since QC is always greater than 0, QH minus QC by QH will be less than 1, that means the efficiency will always be less than 1. Now let us look at the heat pump. So what is a heat pump doing? Heat pump is basically pumping heat from a low temperature reservoir which is kept at temperature TC by consuming external energy WHP, and it is rejecting this heat to a high temperature reservoir TH. So it is taking heat from reservoir at a lower temperature TC and throwing it to a reservoir which is at a higher temperature TH. This vertical axis actually shows the temperature, that means the temperature is increasing in a vertical direction. Okay. Again, if you can apply the first law of thermodynamics to the heat pump, you will find that you can define the efficiency of a heat pump as your useful output divided by the input, and for a heat pump the useful output is the heat rejected to the high temperature reservoir, that means QH. And what is the heat input? What is the energy input to the system? Input to the system is in the form of work. So the efficiency of the heat engine is nothing but QH divided by WHP, and according to Clausius statement, WHP has to be greater than 0, it cannot be 0. So it has to be greater than 0 means the efficiency of a heat engine cannot be infinite. Okay, it has to consume certain finite amount of energy. Now let us look at refrigerator. A refrigerator, what is it doing? It is also doing exactly the same thing as a heat pump, only difference is in the temperature levels. For example, a refrigerator low temperature reservoir is much lower than the ambient, because we want to keep certain products or processes at low temperature. That's why we need a very low temperature TC. So this refrigeration system, a cyclic refrigeration system, what it does is it takes heat QC from the low temperature reservoir, consumes some external